So when we're doing VSEPR, for example, our first molecule, which is xenon tetrafluoride, which is XeF4, we want to draw our typical Lewis structure, which has the xenon in the middle and a fluorine over here surrounding the xenons, 4 fluorines. And then we draw the valence electrons. And we can't forget about that xenon has 8 valence electrons and it only has 4 bonds in this case. So it's going to be having 4 extra electrons right here. And this is the complete balanced model of xenon tetrafluoride. And just a review on how we check that, we can check our center atom, which is xenon, and we can calculate the formal charge. So how do we calculate the formal charge? So xenon has typically 8 valence electrons, and we subtract that by the number of bonds and electrons. So we have 1, 2, 3, 4 bonds and 4 electrons around xenon. So it's just 4 plus 4. And 8 minus 8 is going to be equal to 0. And that kind of tells us that our center atom at least is good. And if we just want to calculate fluorine on top of that, we can do that in our head. Fluorine has 7 valence electrons, and around this fluorine there's 6 valence electrons, and there's 1 valence electrons that is bonded. So it's going to be 1 bond plus 6 valence electrons, which equals 7. And 7 minus 7 equals 0. And all these fluorines are the same, so the net formal charge would be just 0, which is the best way to find this. In terms of VSEPR theory, we first have to start off with the electron geometry. And the electron geometry is found by counting the number of electron groups around the xenon. So the xenon has 1, 2, 3, 4, 5, 6. 6 electron groups. When we have 6 electron groups, the electron geometry is going to be octahedral. And just to go over electron geometries, when we have 2 electron groups, electron geometry is going to be linear. When we have 3, electron geometry is going to be trigonal planar. When we have 4, it's going to be tetrahedral. And you can remember that by the tetra, which means 4. When we have 5, it's going to be trigonal bipyramidal. When we have 6, it's going to be octahedral. So with this list, you can find the electron geometries. So in this case, xenon tetrafluoride's electron geometry is octahedral. Another geometry we must find is the molecular geometry, which is a little more complex in this case. And I personally think looking up one of those charts on Google Images for the VSEPR theory is very helpful in order to memorize these molecular geometries. So I would recommend doing that. But when we have So molecular geometries account for the lone pairs on the central atom. And in this case, xenon has 2 lone pairs. And this is when it gets a little complex. When an octahedral electron geometry has two lone pairs, it's going to be a square planar. And this is once again just due to pure memory and going over the charts, which I would heavily recommend. But one reason I can give in why this is square planar is because when you have an atom over here and when you have four things bonded to it, when you have something pushing down here, these bonds are going to get pushed down. But when you have something over here too, there's going to be net of 0, which makes this a square-like structure. A square planar. That's the best way I can explain it without looking at the chart. For our second example, we have a similar molecule in this case, and it's going to be xenon difluoride. For xenon difluoride, we just draw our typical Lewis structure. And since xenon has 8 valence electrons and only 2 bonds in this Lewis structure, we must draw 6 valence electrons around xenon. So once again, we go to our electron geometry. And in this case, our electron geometry is, so we have 1, 2, 3, 4, 5. We have 5 electron groups. So that means it's going to be trigonal bipyramidal. Sorry, I spelled that wrong. As you can see with the previous thing we drew. When you have 5 electron groups, it's trigonal bipyramidal. For molecular geometry, in this case, once again, it's a little more complex, but this time we have 1, 2, 3. 3 lone pairs around the central atom. And when you have these 3 lone pairs, you're going to get a linear structure, a linear molecular geometry. And once again, the best way I can show that is by drawing atoms. So we have our central atom right here. We have something bonded to it over here. And we have our other atoms. And when you have 2 lone pairs pushing on it, it tends to go down. So this structure could look like this instead, which is in a sense, it's sort of like a bent structure. When you have another lone pair over here, there's once again a net cancellation of this. So it just tends to become a linear structure, a straight line. And I forgot to go to bond angles for the first example. But for the first example, we also must find another aspect called a bond angle, which means the angle of a bond over here. And for an octahedral square planar structure, our bond angle is just 90 degrees. Just think about having a square. A square in this case, this angle would be 90 degrees. So that's one way you can memorize it. In this case, for xenon difluoride, the bond angle would be just 180 degrees. Once again, think about it like a line. This angle would just be 180 degrees, the horizon.